We will carry out an f-test at the 0.05 alpha level to compare the means of these groups. The null hypothesis is that the means of the populations that these groups come from are equal. Let's look at this group here, the control group. Okay, now we will call the mean of the population that this group comes from mu c, c for control. We will call the mean of the population that this group comes from mu L, L for low dose. And finally, we will call the mean of the population that this group comes from mu H, H for high dose. As an aside, the assumption underlying the f-test is that these groups come from normally distributed populations with equal variances. So we don't know what the variances are, but the assumption is that the variances are the same. So sigma c squared is the variance of the population that the control group comes from. So this is one of the assumptions of the f-test. And also that the three populations are normally distributed. First, we get estimates for the unknown population means mu c, mu L and mu H. Those estimates are sample means. So we get the mean of the control group. We just sum these 5 numbers and divide by 5 to get 7. Similarly, we get the mean of the low dose and high dose groups. Now we are going to look at variation between the groups and also variation within each group. One of the statistics that we need is the variance of each group. So up here I'm showing the standard deviation of the control group, S sub c. This is a variation of the values within the control group about their mean. The mean is 7. So we have to get the squared deviation of each value in the control group from the group mean, which is 7. So that involves getting a measure of spread. So 9 minus 7 is the distance of 9 from 7. And we square that, and then we do the same for 6. Get 6 minus 7 and square it, and so on to the last value, which is 8. So on top we have 5 squared deviations. We get a mean of those. We don't actually divide by the number of deviations. We divide by the number of deviations minus 1. You see, this is a sample standard deviation. We are using SC as an estimate for the unknown standard deviation sigma c. That's the standard deviation of the population that the control group comes from. And it turns out that by subtracting 1, we get a better estimate of sigma c than we would if we just had divided by 5. Okay, so in general we divide by n minus 1. So here's the general formula. This uppercase sigma means we sum what comes after it. I runs from 1 to little n, where little n is the number of values in the sample. Little n is 5 in this case, so we have 5 squared deviations. Xi is just each value, that's 9 to 8. X bar is the mean, which is 7, and so on. Okay, if you do this in your calculator, press the S button, you know, you'll have the standard deviation, but if you want the variance, you'll have to square the result. So for the first group, the variance is 2.5. Okay, and I've written down the sample variances of the next 2 groups as well. Now, 2 other statistics that we need are the grand mean and the grand variance. The grand mean is the mean of all 15 values. So we could take all 15 values, sum them and divide by 15. However, we have the same number of values in each group. So a quick way to get the grand mean is sum the 3 group means and divide by 3. That will give you 5 1/3. We can only do that if we have the same number of values in each group. Now, to get the grand variance, we cannot sum the 3 group variances and divide by 3. We have to actually feed all 15 values into the calculator. Press the S button, which will give the standard deviation. Square the result, and you should get 3 and 20/21. Here we have a scatter plot of the number of errors committed by each subject. So in blue I'm showing the control group. The mean number of errors in that group is 7. The sample variance, as we saw, is 2.5, so that's a measure of spread of these blue dots around this horizontal blue line. We can also see the low dose and high dose groups. Included is the grand mean, which is 5 1/3. The first source of variation that we will look at is the variation of all 15 subjects about the grand mean. So we'll be getting the distance of each value from the grand mean. That's the deviation, taking each value and subtracting the grand mean. And we do that for all 15 values. So for example, this value is 9. The number of errors committed by one of the subjects in the control group. So we will be taking 9, subtracting the grand mean, which is 5 1/3. That gives us the length of this line. Now this could be positive or negative, depending on whether the point is below the grand mean or above it. So we square it to make it positive. We do this for all 15 values, and we sum all those square deviations. So what we then get is the total sum of squares, written SST for sum of squares total. So if we go back to the table here, the first value is 9, so we have 9 minus 5 1/3 squared. Then we have 6 minus 5 1/3 squared, and so on as far as the last value, which is 6. So the last value will be 6 minus 5 1/3 squared. So we've the sum of the square deviations of all the values about the grand mean. Now if you work out these 15 square deviations, you get 55 1/3. Now there's a much quicker way of doing this. Earlier we calculated the grand variance, which we called S squared. We got 3 and 20 over 21. So here is the grand variance. So how do we calculate the grand variance? Well, you could do it on the calculator, but what does the calculation involve? It involves taking each value, each of the 15 values, subtracting the grand mean and squaring, and summing all those square deviations. Finally, you need to divide not by 15 but by 15 minus 1. We subtract 1 for because we want S squared to be an unbiased estimate of sigma squared. But anyway, we don't have to worry about that. So what the calculator did is, but you can see that that's very close to what we're after. If we look at the numerator here, everything on top is SS total. That's what we want. So we're just one small step away from getting SST. So if we know this thing, which we get from our calculator, we only have to multiply it by the denominator, which is 14. So we're after SS total, so that's what's on top. SS total divided by 14 is the grand variance squared. So SS total is 14 multiplied by the grand variance. So it's 14 times 3 and 20 over 21. And that's 55 1/3. So the grand variance looks like the grand standard deviation without the square root sign. Symbolically, sum of squares total looks like this. This is an uppercase sigma. It means that we sum what comes after it. So we have to sum each value minus the grand mean squared, and that's exactly what we did. And we sum from over the number of values. Capital N here is the number of values, as opposed to small n. Small n is the number of values in a group. So capital N in our case is 15. So we have 15 square deviations. Xi just stands for each value. So x1 would be the first value, which is 9. x2 would be the second value, and so on. As far as x15, the last value, which is 6. And of course the grand mean x bar bar is 5 1/3. The grand variance, symbolically, is this quantity, SS total, divided by the number of values minus 1. So we use capital N for the total number of values. So I'll go back to writing capital N here. And you can see that in general, if we want SS total, and if we know S squared from the calculator, we multiply S squared by the total number of values minus 1. Next, we are going to consider variation between the groups. Now, this involves a sum of squares calculation. Sum of squares between. Another term that's used is sum of squares model, because we are going to model the values in each group on the group mean. So let's see what that means on the scatter plot. The group mean for the control group is 7. So we're going to model each value by 7, by the mean of the group. So we're going to pretend that all of these values are equal to the group mean, which is 7. Well, this value is equal to the group mean. Next, we will get the variation of these values about the grand mean. So that involves the distance of the group mean for each of the 5 values from the grand mean, represented by these vertical lines. We do the same for the other 2 groups. So we model the values in this group by the group mean, which is 5.2. So we imagine replacing each of the values in this group by 5.2. And we get the distances of them about the grand mean. So we get these vertical lines. So let's see a calculation. How do we get one of these lines? Well, you see, we have to take the group mean, which is 7, and subtract the grand mean, which is 5 1/3. Okay, so each of these values is 7, and subtract 5 1/3. If you simply subtract, you'll get a distance. To ensure that this thing is positive, you need to square it. Because, you know, if points are like below the line, like they're in the next group, actually, if you take 5.2 and subtract 5 1/3, you'll get a negative value. But squaring ensures that it's positive. So we have the squared lengths of these lines. Now this is done 5 times. So, you know, there are 5 values to consider here. We're modeling each value by the mean of the group. So you have 5 of these squared deviations. So you have to multiply this by 5. And we have to do the same here and here. Okay, so this is the sum of the squares for the first group. And we have 5 such lines to consider for the second group. Let's see the mean of the second group again. It's 5.2, so it's 5.2 minus 5 1/3 squared. Finally, for the last group, the mean is, we model all the values by the mean of the group, which is 3.8. Get the deviation of them from the grand mean, subtract 5 1/3, square it to ensure that it's positive, and 5 such square deviations, so we multiply by 5. Symbolically, this calculation, which is quite straightforward to do, can be written like this. What we're doing is we are summing over the groups. So I here, the subscript I, runs from 1 to the number of groups, which is often denoted by k. So in our example, k is 3, so we have 3 square deviations. Small n sub I is the number of values in each group. Now in the example that we did, the number of values in each group is the same, it's 5. xi bar is the mean of each group. So it's 7 for the first group, 5.2 for the second group, 3.8 for the third group, and of course x bar is the grand mean. Okay, you can see that we have a common factor of 5 here, so before you go to your calculator you can just factorize out that 5 and just plug all this into the calculator. You should get 25 and 11/15. Finally, the last source of variation that we consider is the variation within each group. This is written sum of squares within, or sometimes sum of squares or, where R stands for residual. So let's see what this source of variation looks like on the scatter plot. So we are going to get the variation of the values in each group about the group mean. So we're going to get the distance of each value from its group mean. It's represented by these vertical lines. The distance of this value from the group mean is 0 because it is equal to the group mean. We do the same for each group. So what do we have to do? Let's look at this one here. This value is 9, so we have to get 9, subtract 7, and square. So we have to repeat this for all the values. Okay, subtract 7 from all the values and square, and sum the square deviations. Well, of course, the length of this line is 9 minus 7, but part of the problem involves squaring to make sure that we get a positive result. So if we do the subtraction for this one here, we get 6 minus 7, which is minus 1, so squaring it will make it positive, plus 1. So let's look at the groups. In this group, one value is 9, the first value is 9, the last value is 8. So we've 9 minus 7 squared as far as 8 minus 7 squared. That's for the control group. Okay, I'll just separate that out here, bracket it out separately. And next thing we look at low dose group. So we'd have to get 7 minus 5.2 squared as far as 5 minus 5.2 squared. Finally, for the high dose, we're starting with a value of 5, subtracting the mean, which is 3.8. Now it turns out that we don't actually have to do this calculation at all. We have 3 sums of squares, and the 3 sums of squares are related. The sum of squares total is equal to the sum of squares between plus the sum of squares within. Now for the F test we need both of these. So we normally calculate sum of squares total and sum of squares between, and we just subtract to get sum of squares within. You see, both of these calculations are relatively straightforward, SST and SSB. So from this we see that SSW is sum of squares total minus sum of squares between. And we have those values. If we go back up here for sum of squares total, we got 55 and 1/3. So we have 55 and 1/3 minus 25 and 11/15. You will get 29 and 3/5 or 29.6. Now that's the quickest way to get SSW. You could still go and work out these using a shortcut involving the variance of each group. You don't actually have to work out all 15 of these square deviations on the calculator. You see, you can use the variance, the sample variance of each group, these 3 numbers, to greatly reduce that calculation if you want to do that calculation directly. You see, this thing here comes from SC squared. It's actually SC squared multiplied by 5 minus 1. See, when you're calculating SC squared, you're summing the square deviations and dividing by the number of values minus 1, 5 minus 1, so you can reverse that. So if you multiply SC squared by 4, you'll have the result in here, and similarly multiply SL squared by 5 minus 1 or 4 to get this one, and finally multiply SH squared by 5 minus 1. But I think it's quickest just to use this rule here. SST is SSB plus SSW. Of course, if you do it both ways, you can check that you should get the same answer of 29.6. We summarize our results using an analysis of variance or ANOVA table. So in this column we have the source of variation. So we have variation between the groups, SS between, or also known as SS model, because we model each value in each group by the mean of the group that the value is in. We have variation within each group, that's SSW, or also known as SS residual, SSR, and we have SS total. Okay, so if you know any 2 of these values, you can get the third value, because SS between plus SS within equals SS total. Now MS stands for mean sum of squares. So when we calculated, say, SS between, we calculated 3 sums of squares. Okay, I won't bother writing it out again, but you know, we had three sums of squares. We had the mean of the first group minus the grand mean squared, plus the mean of the second group minus the grand mean squared, plus the mean of the third group minus the grand mean squared. Now the thing is, if we knew what the grand mean was, 5 1/3, we would only have two calculations to do. So if we didn't know the grand mean, we would have 3 degrees of freedom. But because we know the grand mean, we have 1 less than 3 degrees of freedom, or 2 degrees of freedom. Actually, in general, the degrees of freedom for sum of squares model is the number of groups minus 1. So in our case, we get 2. To get the mean sum of squares, we take 25 and 11/15. So this is the mean sum of squares for model. Okay, MSM you can say, is the sum of squares for the model. I'll just write it down first. Divided by the degrees of freedom. So it's going to be 25 and 11/15 divided by 2. I've decided to put in a degrees of freedom column here. Okay, so number of groups minus 1 is 2. 25 and 11/15 divided by 2 is 12 and 13/15. Now, what about SSW? Well, actually, it's probably easier to get the degrees of freedom for SS total. It's easier to see where that comes from. Because it turns out these 2 degrees of freedom will add up to the degrees of freedom for SS total. So let's go back to SS total. What do we do to calculate that? Well, we just took each value, starting with 9 actually, and subtracted the grand mean, which was 5 1/3 squared. And we did that for all 15 values, whatever the last value was. So there was 15 square deviations. So if we didn't know the grand mean, we would have 15 degrees of freedom, 15 independent calculations. But it turns out that we have only 14 independent calculations because we know the grand mean. So for example, we could do 14 of these calculations and work out the 15th. But anyway, we don't really need to know too much about where the degrees of freedom comes from. We just take, for SS total, we take the total number of values, which is 15, and subtract 1. Okay, so we just take 2 from 14 to get the degrees of freedom for sum of squares within. If you want to get this directly, you just have to realize that we lose 3 degrees of freedom when we calculate sum of squares within. Okay, because we have 15 square deviations to work out for sum of squares within, but those calculations involved 3 group means. So we get the total number of values and subtract the number of groups. The total number of values is often denoted by capital N. The total number of groups is denoted by K. So in general, the degrees of freedom for sum of squares total is capital N minus 1. The degrees of freedom for sum of squares between is K minus 1, number of groups minus 1. And this thing here is N minus K. If you add K minus 1 onto N minus K, the K's will cancel and you will be left with N minus 1. Now finally we need the mean sum of squares, so we need to take 29.6 and divide by the degrees of freedom, which is 12. You will get 2 and 7/15. Divide this by this. Next we calculate what is called an F value for the groups. So that's mean sum of squares between divided by mean sum of squares within, or if you use the other notation, mean sum of squares model divided by mean sum of squares residual. The value that you will get is 5.22. Now, under the null hypothesis that the groups come from populations with the same mean, and of course we are assuming that the populations are normally distributed with equal variances, it can be shown that this ratio MSB over MSW follows an F distribution. Now there are 2 parameters to the F distribution. The first parameter is the degrees of freedom for MSB, which we know is 2. And the second parameter is the degrees of freedom for MSW, which we know is 12. Okay, so the first parameter is the degrees of freedom associated with the numerator, and the second is the degrees of freedom associated with the denominator. F distributions are skewed to the right. The smallest value that this quantity can have is 0. Okay, so values of this quantity lie along the horizontal axis. You can see from the distribution that most values should be in around here where the peak is. Very few values should be along here, okay, because the distribution is tailing off here and the probability is small of getting values along here. So the critical region in our problem is the region for which the probability is 0.05. So that's the 5% level that we are working with. So the probability of getting a value of this thing that's along here, anywhere along here, greater than this value here known as the critical value, is 0.05, 5%. So we need to look up F distribution tables for alpha equals 0.05. So we want this area to be 0.05. So the first parameter, written degrees of freedom 1, is 2 in our case. The second parameter, df2, is 12. So we go along to 2 across the top here, and we go down to 12. And that'll give us this value here, the critical value. So if we do that, you see we get 3.8853. So the next thing that we do is we look at the F value that we got, 5.22, and compare it to the critical value. If it's greater than the critical value, we reject the null hypothesis. Okay, that's the case here, of course. 5.22 is in the critical region. It's along this black line here. So we reject the null hypothesis that the means of the distributions are equal. Or sorry, the means of the groups are equal. Well, actually, what I said was correct. If the distributions, the underlying distributions must have, well, they don't have to have, but under this test, we reject the hypothesis that the underlying distributions have equal means. So remember, this was the null hypothesis. So this is what we reject. To get a rough understanding of what's going on here, notice that we reject, if we get a high F value, we have a good chance of rejecting. The F value runs from 0 up to, well, infinity in theory. So high F values could be out here in the, if it's high enough, the F value could be in the critical region, the 5% critical region. So what makes an F value high? Well, if the numerator, the sum of, which comes from sum of squares between, this is the variation between the groups, is greater than the variation within each group. Okay, if the numerator is greater than the denominator, well, ultimately this comes from sum of squares between. If sum of squares between is greater than sum of squares within, well, the F value the F value will be greater than 1. And if this is much greater, you know, if sum of squares between is much greater than SSW, it will push the F value further and further away. Sum of squares between is a measure of variation of the group means about the grand mean. So if the group means are far apart, then sum of squares between will be high. So if that's high, then MSB will be high. If there's very little variation within the groups, within each group, then SSW will be low, and so will MSW. So if the numerator is high and the denominator is small, then the F value will be high. We need a high F value to reject the null hypothesis.